Why can't we unify quantum mechanics and general relativity? Hello and welcome to this video where we'll be exploring the fascinating topic of why we can't unify quantum mechanics and general relativity. The quest for a unified theory of nature is one of the great challenges of modern physics. For decades, physicists have been struggling to reconcile the two pillars of modern physics, quantum mechanics and general relativity. While these two theories individually have proven to be incredibly successful at describing the physical world, they appear to be fundamentally incompatible with each other. This article explores the challenges in unifying these two theories, the attempts and ideas proposed to solve the problem, and the implications of a successful unification for the future of physics. Introduction to Quantum Mechanics and General Relativity. Quantum mechanics and general relativity are two of the most important and successful theories in physics. Quantum mechanics deals with the behavior of matter and energy on a microscopic level, while general relativity describes the behavior of gravity and the structure of the universe on a cosmic scale. Despite the fact that both theories have been incredibly successful in explaining a wide range of physical phenomena, they are fundamentally incompatible with each other. The incompatibility of quantum mechanics and general relativity. Understanding the problem. The problem with unifying quantum mechanics and general relativity lies at the heart of their different approaches to understanding the universe. Quantum mechanics is based on the idea that particles do not have definite properties until they are observed. On the other hand, general relativity asserts that space and time exist independently of anything that might be placed in them. Trying to reconcile these two ideas has led to a number of conceptual and mathematical difficulties. The conceptual differences between the two theories. In addition to the fundamental differences in their approaches, quantum mechanics and general relativity rely on different mathematical frameworks. Quantum mechanics relies on complex numbers and probability theory, while general relativity is based on differential equations. This means that merging the two theories requires developing a new mathematical framework that can incorporate both sets of principles. Attempts to unify quantum mechanics and general relativity. Historical efforts to unify the theories. Efforts to unify quantum mechanics and general relativity have been ongoing for many years, but progress has been slow. The earliest attempts to merge these two theories date back to the 1930s and 1940s. These early efforts focused on trying to quantize gravity, but they were not successful due to the problems posed by the mathematical framework of both theories. The emergence of quantum gravity. In the 1980s, a new field of physics known as quantum gravity emerged. Quantum gravity attempts to reconcile the theories of quantum mechanics and general relativity by describing the behavior of gravity in terms of quantum particles. Despite many years of research, however, a comprehensive quantum theory of gravity has not yet been developed. String theory as a candidate for unification. One of the most promising approaches to unifying quantum mechanics and general relativity is through the use of string theory. String theory is a theoretical framework that describes all particles in terms of tiny, one-dimensional strings. While string theory has yet to be proven, its mathematical framework has shown promise in reconciling the differences between quantum mechanics and general relativity. Quantum gravity and string theory. What is quantum gravity? Quantum gravity is a theoretical framework that attempts to reconcile the principles of quantum mechanics and general relativity by describing the behavior of gravity in terms of quantum particles. The idea behind quantum gravity is that gravitational force is carried by particles known as gravitons. Overview of string theory. String theory is a theoretical framework that describes all particles in terms of tiny, one-dimensional strings. These strings vibrate at different frequencies, giving rise to different particles. String theory has shown promise in merging the principles of quantum mechanics and general relativity, but it has yet to be proven experimentally. Implications of string theory for unification. If string theory is proven to be correct, it would provide a unified framework for understanding the universe at both the quantum level and the level of gravity. This would represent a major breakthrough in our understanding of the fundamental laws of nature. However, many physicists remain skeptical about the viability of string theory due to the lack of experimental evidence supporting it. Challenges in developing a unified theory. The quest to unify quantum mechanics and general relativity has been ongoing for decades. Despite numerous efforts by physicists, a theory that merges the two has not yet been developed. The road to unification has been fraught with challenges, including both technical and philosophical obstacles. Technical obstacles in unifying quantum mechanics and general relativity. One of the main technical obstacles to unifying quantum mechanics and general relativity lies in the fundamental difference between the two theories. Quantum mechanics explains the behavior of particles on an atomic and subatomic level, while general relativity is used to describe the behavior of larger objects, such as planets and galaxies. The two theories also use different mathematical frameworks, with quantum mechanics relying on probabilistic equations and general relativity relying on the mathematical concept of spacetime. This difference in mathematical methods makes it difficult to reconcile the two theories. Philosophical obstacles in unifying quantum mechanics and general relativity. Philosophical obstacles also stand in the way of unification. Quantum mechanics suggests that reality is fundamentally uncertain and indeterminate, while general relativity implies that the universe is deterministic and follows strict laws of cause and effect. Combining these two concepts would require a new understanding of the nature of reality. Additionally, the two theories have different notions of space and time. General relativity sees spacetime as a smooth continuum, while quantum mechanics suggests that spacetime is a discrete network of particles. These differing views make it challenging to merge the two perspectives. The problem with experimental verification. Verifying a unified theory is also problematic. Both quantum mechanics and general relativity have been verified in different contexts, but it's challenging to test a theory that combines both. Creating experimental conditions that would allow physicists to confirm the predictions of a unified theory is a significant challenge. Implications of a unified theory of quantum mechanics and general relativity. Despite these obstacles, a unified theory would revolutionize our understanding of the universe. It would provide a complete and consistent description of the physical world, explaining both the behavior of tiny particles and the movements of massive objects like stars and galaxies. Philosophical implications of a unified theory. A unified theory would also have profound philosophical implications. It would provide a new understanding of the nature of reality, resolving the apparent contradictions between quantum mechanics and general relativity. A unified theory could also shed light on the fundamental nature of space and time and provide new insights into the origins of the universe. Practical implications of a unified theory. Practically, a unified theory would have far-reaching implications, enabling us to build supercomputers, develop new technologies, and even explore new frontiers in space. A unified theory could provide a deeper understanding of the universe and enable us to tackle some of the most significant challenges facing humanity. Future directions in the search for a unified theory. Despite the challenges, physicists continue to search for a unified theory of quantum mechanics and general relativity. Latest developments in the field. Recent developments in the field include string theory, loop quantum gravity, and causal dynamical triangulation. Each of these theories offers a unique approach to unify the two frameworks. Promising ideas for unification. One promising idea is the holographic principle, which suggests that all the information contained in a three-dimensional space can be represented as a two-dimensional surface. Another is the idea of emergent spacetime, where spacetime is seen as an emergent property arising from the interactions between quantum particles. Directions for future research. Future research in the field will focus on developing methods to combine the mathematical frameworks of quantum mechanics and general relativity and testing these theories experimentally. Advancements in technology, such as supercomputers and particle accelerators, will play a critical role in this research. Conclusion: the quest for a unified theory continues. The search for a unified theory of quantum mechanics and general relativity has been a daunting task for physicists. However, recent developments in the field offer hope that someday a unifying theory will be discovered. A successful unification would revolutionize our understanding of the universe and have far-reaching implications for technology and society as a whole. In conclusion, the unification of quantum mechanics and general relativity remains one of the greatest challenges in modern physics. Despite the significant progress that has been made over the years, we are still far from achieving a complete and satisfactory theory. However, the continued efforts of physicists and scientists around the world give us reason to remain optimistic that a unified theory of nature may one day be achieved. The challenge is immense, given the different scales involved and the incompatibility of the two theories' mathematical frameworks. However, the search for a unified theory remains ongoing, and scientists continue to explore new approaches to bridge the gap. The unification of these two theories would be a huge step forward in our understanding of the universe's fundamental nature, bringing about a new era of scientific understanding. We hope you enjoyed this video and learned something new. Thank you for joining with us. Thanks for watching.